Hello, good evening to all of you.
Good evening, sir.
Good evening, sir.
Good evening. Good evening. Am I audible?
Yes, sir. Audible.
Okay. Is my screen visible to you?
Yes, sir.
Okay, please answer your reference. Aditya Kumar,
Present, sir.
Anand,
Yes, sir.
Ananda Kumar,
Yes, sir.
Arnachalam,
Yes, sir.
Hasan,
Present, sir.
Hemant,
Present, sir.
Jagan,
Yes, sir.
Kesav Prasad,
Yes, sir.
Lakshmi Narayanan,
Sir.
Prabhakaran,
Present, sir.
Prem Vinayak,
Present, sir.
Rahul,
Yes, sir.
Rajan Kumar,
Yes, sir.
Sabish Kumar,
Present, sir.
Satish Kumar,
Present, sir.
Titus,
Present, sir.
Valish,
Yes, sir.
Vigneshwaran,
Present, sir.
Vijay Raj,
Yes, sir.
Vikas,
Present, sir.
Vivekanand, Vivekanand,
Present, sir.
Yadav,
Yes, sir.
Yuvraj.
Present, sir.
Fine. So today there are no absentees. I have sent you the material, all my lecture notes and lecture slides for chapter 3 and 4. Have you received it?
Yes, sir. Yes, sir. Yes, sir.
Okay, so you can use this as a reference for preparing your quiz 2, which is by next week, right? Next Saturday.
6th of April.
Okay. So the syllabus for quiz 2 I have already told, chapter 3 and 4. Whatever we discuss after chapter 4 will be included for your end semester exam. For quiz 2, you go through chapter number 3 and 4. SI and CI engine combustion, and chapter 4 on instrumentation to study the combustion process. Are there any questions related to that?
Professor, sir, can I ask a repeat question? I'm sorry, probably I could not understand it well. The assignment 2, question number 1, sir. In which the second part of the question, when the combustion chamber is modified to which type and plug is located to the mean of the charge in that sense. So if you want to comment about the knocking tendency of that, so do we want to compare it with some other type of combustion chamber or standalone in that sense? What I mean to say is, like engine is having some combustion chamber which is changed to this, or I would say like it's a standalone.
Second, I'm just opening the question. So your doubt is on question number
1B, question number 1, part number B.
Okay.
Ji sir.
Question number 1, part B, wedge-shaped combustion chamber with a spark plug located at the center of the effective combustion space.
Right, sir.
Comment on the knocking tendency. Increase or decrease. So compared to a standard combustion chamber, if you have a wedge-shaped combustion chamber with a spark plug located at the center of the effective combustion space. So what is asked, what is expected from this question is, if you have designed a combustion chamber like this, if you have designed a combustion chamber having a wedge shape, okay, wedge shaped cylinder head with a spark plug located at the center, comment on the knocking tendency of this particular combustion chamber, whether it will be high or low, or in other words, increase or decrease. You have an SI engine, you have designed a combustion chamber of this geometry, okay. with the spark plug located at the center, you are asked to comment on the knocking tendency of this particular combustion chamber.
Noted, sir. Okay, sir.
Whether the knocking tendency will increase or decrease with this combustion chamber. That's it.
Noted, sir. Thank you.
In fact, you are not comparing anything here. You have to comment on if you have such a combustion chamber design, whether the knocking tendency will increase or decrease.
Noted, sir. Thank you.
Okay, fine. Any other questions you have? Okay, so there are no questions. Welcome back. So this is we are in chapter 4 now. We are now discussing about the instrumentation to study the combustion process in engines. Okay. So here we previous class we discussed about the pressure measurement and crank angle measurement. So one of the fundamental data or the critical data that you need to have to analyze the combustion process in IC engine is cylinder pressure profile that shows how the in-cylinder gas pressure varies with crankshaft angular position called as crank angle. So we will observe how the pressure varies with crank angle. Okay. And this is one of the important data, fundamental data that you need to have to analyze the combustion process in IC engine, cylinder pressure profile. So that's why we discuss how to acquire this pressure, in cylinder gas pressure, what instrument you need, what is the measurement principle followed. That's what we have discussed. And also we discuss what instrument is required to acquire the crankshaft angular position and what is the measurement principle involved. One thing as we have discussed here is when you talk about angle measurement, you need a reference point. The reference point in angle measurement, crank angle measurement, is the compression TDC position. So we need to know how to get precisely this compression TDC position because the angle measurement start with having compression TDC as a reference point. Okay, so today I'm going to start with a discussion on how to get the compression TDC position so that we can count the angle. Angle count start with taking compression TDC as a reference. For example, we generally consider compression TDC as a 0 angle. Any angle measured after that, any angle after that will be considered with a positive sign. Any angle before that, that is during compression stroke, it will be considered with a negative sign. This is a standard nomenclature followed to indicate the angle, crank angle. So the reference point is important here, the compression TDC position. So now let us look at how we can get this compression TDC position. Before that, so what is shown here on the left hand side, you could see a plot that shows how the pressure, in cylinder pressure and volume varies with the crank angle. Okay, so this one is the pressure profile. It shows how the pressure varies with crank angle, and second one is the volume, in cylinder volume, instantaneous volume, right? How the volume varies with angle, crank angle is shown. Okay, we are in fact overlapping the pressure profile and volume profile in the same plot, and pressure and volume variations are shown here with respect to crank angle. So one of the important observation you could make here is there is a minimum volume, and this pressure whatever I have shown is acquired under motoring condition, that is unfired condition. Okay, one of the important information you could observe here is so the volume, as you know, this is compression minus 180 degree to 0 degree. This is the compression process. Then from 0 degree to plus 180 degree is the expansion process. So there is a compression process here and there is an expansion process here, and compression TDC is a reference point. Volume, you know, when during the compression process, the volume will start to decrease, reach a minimum volume, and then during expansion, the in-cylinder volume is going to increase gradually. Okay, reaches a maximum at 180 degree. Okay, and what will be the minimum volume point here? When the volume will be minimum?
Clearance volume, sir.
Clearance volume.
Clearance volume, or that is a minimum volume point is the TDC position, right?
Right, sir.
Minimum volume point is the TDC position. That is where you get the so this is the minimum volume. This is volume at TDC, which is nothing but clearance volume, as you rightly said. This is the clearance volume, right? This minimum volume corresponds to the piston TDC position. But what you can also see by looking at the pressure profile, This is a maximum pressure or peak pressure as indicated here. This peak pressure do not occur at TDC point, rather it occurs at some angle before the TDC. So you could see here, this is a Pmax Pmax point in the sense angle. The angle at which the maximum pressure occurs is happening here at some angle before the minimum volume point. Minimum volume point is where the TDC is located, and this is a location of the Pmax, maximum pressure occurrence. So maximum pressure occurs at some angle before the minimum volume point. Minimum volume point is the TDC point, right? So one would expect that the Pmax will happen at the compression TDC point, because that is where the maximum compression effect is there, right? Air, if you consider this as a motoring profile, you are compressing air. You would expect that the maximum pressure of the air will occur when the piston is at TDC point. But rather, you could observe here that the maximum pressure is happening at some angle before the piston reaches TDC point. At TDC point, the pressure is in fact slightly lower compared to the pressure before TDC. Can you tell me the reason for this? Suppose if the Pmax and V minimum coincide with each other, then it is a straightforward thing to determine the compression TDC, because minimum volume and Pmax are aligned. If Pmax occurs at the minimum volume point, compression TDC position is straightforward. But this is not so. You could see that it happens at some angle, some crank angle before the TDC point. So what could be the possible reason for Pmax happening at some angle before TDC point?
Will be like after like once the piston reaches the TDC point, no, that piston certain crank angle, it will be in the TDC position only, because it is not a single point to reach and then come back. So that is the reason what once it is reaches, then it will have certain angles, will have the same like piston will be remain same, but the theta will be some, for example, 4 degree.
So you are saying that the piston will stay at TDC for some time?
Some 2-3 months, 3-4 degrees. Yes.
No, why should it be? Because the crank is continuously rotating, right? Since the crank is continuously rotating, it should not allow the piston to stay at any point. Did you get what I am saying? Piston is connected to the crank through the connecting rod and arm, crank arm. Crank shaft is continuously rotating. It won't allow the piston to stay at any point.
Temperature would have reduced.
What is it? So my question here is why the Pmax is not happening at TDC?
Yes.
Rather, it is happening at some angle before TDC. Question number 1. Question number 2, at TDC, there is some drop in pressure. It is not maximum. Why so?
Sir, is that because when the piston is approaching TDC, so basically still the gas is moving like through the valve, gas is flowing and it is hitting the piston in downward direction. So once the piston is moving up, so at that time, crevice volume is not getting filled at the time. So once the piston is getting exactly at TDC, what is happening is the mass of the the volume of the gas level for the piston, it will squeeze to the it will leak through the rings basically, and hence
very good.
Hence,
so there is some mass loss.
Exactly, sir. So hence it will be loss of some pressure. But before it reaches TDC, it doesn't have time to leak through the piston because it is giving the momentum towards the up. What I mean to say is in that way. So that is my understanding, sir. Probably.
Okay. No, it's a good observation. Anything else? So there is some. So I will summarize what you said. There is some loss of mass at TDC, which is causing the drop in pressure. Right?
Precisely that, sir. Right, sir.
Yes. Anything else?
Temperature loss. Temperature loss.
Temperature. Related to temperature, what is that you want to say? Related to temperature. You have not
temperature loss because of fuel injection.
No. This is motoring. Motoring means you are compressing only air. No fuel injection. Related to temperature, what will happen with respect to temperature? Since you have not insulated the engine, what will happen with
heat loss will happen, sir. Heat loss,
because of which
heat loss, right?
Heat loss will happen, yes, sir.
Where the heat loss will be maximum?
quenching at the end of the
Can I say at TDC point heat loss is maximum?
Right, sir.
Because that's where the compression is maximum, right? So to summarize, why Pmax is not happening at minimum volume point or TDC point is, at TDC point there is some loss of pressure, right? It drops below the Pmax. And the associated angle is called thermodynamic loss angle. You could see that this angle, the shift in angle where the Pmax is happening is referred to as thermodynamic loss angle. This is because of thermodynamic phenomena. At TDC point, there are two things that are happening. One is there is loss of mass, as you rightly said. Second one, the heat loss is also maximum. There is loss of mass when the piston compresses the air. When the piston compresses air in the cylinder, there will be loss of mass. Where is that mass going? It is crevice flow. Okay, we already discussed about crevice flow. When the piston moves up and compresses the air is here. When the piston compresses air, the air pressure increases. When the air pressure is higher, it will start, some mass will flow wherever you have a dead pocket. One of the major dead pocket in the cylinder is the crevice. Okay, this is a small clearance, radial clearance we discussed earlier. Because of the small radial clearance in this region, so there will be flow of mass from the cylinder to the clearance that is available between the piston outer surface and the cylinder liner. So some air mass will go and fill in that available space. And this is what I mean by mass loss, because mass is not contained here. You have to note down here that the magnitude of pressure in the cylinder is also a function of mass of air in the cylinder. Since you are losing some mass, and that mass loss is maximum when the piston is at TDC point. At TDC point, the loss of mass to the crevice is maximum because that is the point where the piston compresses air to the maximum extent. Air is compressed to a maximum extent at TDC point. So loss of mass through the crevice flow is also maximum at TDC point. This is one effect. Second one, since you have not insulated the engine, there is a heat loss. Okay, heat loss is a function of temperature gradient, right? You know, especially by convective mode, it is a function of temperature gradient. This temperature reached in the cylinder is maximum when the piston is at TDC, where the compression effect is highest. At the highest compression effect, you will have Tmax happening, and this happens at TDC point. So this happens at TDC point. Tmax is there. Because of that, the heat loss is also maximum. Because of the maximum temperature in the cylinder, the heat will be lost to the coolant circulated in the coolant jacket, cooling water flow jacket. You are circulating a cooling medium, generally water, that absorbs the heat from the air. So there is loss of energy through heat loss. There is loss of mass to the crevice. All these effects are maximum. These effects will happen, continue to happen when the piston start moving up. Okay, but what is happening at TDC? These effects are maximum. Loss of mass is maximum. Heat loss is also maximum. To sum up, because of these two losses, the Pmax is not happening when the piston is at top dead center position. Rather, it is happening at some angle before the piston reaches TDC. At TDC point, there is some loss of pressure. So you could see that it is just below the Pmax value. And this loss of pressure is primarily due to mass loss and heat loss, just now I discussed. So overall important point to note down from the pressure volume plot here is the minimum volume, that is the TDC point, and the maximum pressure do not coincide. Because of this, you need to carefully determine the compression TDC point. We have already discussed that in the angle encoder, you have two markings. One is the incremental track mark, where you are tracking the angle. Crankshaft angle corresponds to the incremental track. Okay, and there is one reference mark, which is a compression TDC mark. So you need to inform this device when the piston reaches compression TDC point, meaning this mark has to be aligned with the actual piston TDC position, compression TDC position. Okay, otherwise your measurement will go wrong. I mean, TDC reference point will go wrong. So this is what we are determining here. This is what I mean by compression TDC determination. Okay, so now let us look at how to get this compression TDC point. there are two methods. Okay, so there are two methods here for determining compression TDC. One of the method is called static method. This is determined when the engine is at rest. You are not running the engine. That is a static method. Second one is called dynamic method. Dynamic method is done when the engine is running, not under fired condition, rather during motoring condition. So engine is motored to get the compression TDC point. Motoring is unfired condition. So here this method of determining TDC is done when the engine is at rest. It is not running. Okay, that's why it's called static method and this is called dynamic method. Among these two methods, this is more accurate. Dynamic method is more accurate. Rather, static method is straightforward, simple. You don't need any additional device. Now let us first look at how to get compression TDC from the static method. So what you will do here in the static method is you are going to do two markings in the flywheel. Okay, so point number 1 and point number 2. Two markings are going to be made in the flywheel. This is point number 2. This is point number 1. And these two markings are made for the same piston height. For the same piston height. Okay, piston vertical position. We are considering a vertical engine here for the same piston vertical position. Right, so you are going to make one mark. Point number 1 here. Right, when the piston is before TDC. So 1 is before TDC, before the piston reaches TDC, and the same at the same elevation. This is point number 2, and this you are going to mark in the flywheel after the piston moves down from TDC. So point number 1 is made when the piston is moving up at a height, particular height here, and point number 2 is made in the flywheel when the piston is moving down and reaches the same height. Okay, so this is your TDC which we want to determine. We are making two marking, 1 before the piston reaches TDC at the particular height, 2 after the piston moves down from TDC at the same height. So these two markings are made in the flywheel. Now when you bisect this angle, so you are getting an angle here. When you bisect this angle, right, you will get the exact TDC point. So the angle will bisect at the TDC point. Okay, so this is how you get the static TDC, compression TDC under static method. Okay, and this is based on eye judgment. Eye judgment, that's why it is not an accurate method, as I said, because it's based on your eye judgment. Rather, accurate method is done using a device which is called capacitive proximity sensor. So you need to use this device to get the accurate piston TDC point. So what you do in this method, you are going to motor the engine. Okay, so this sensor, capacitive proximity sensor, consists of two conducting elements. One of the conducting element is a sensor that is fixed in the cylinder head. The other conducting element is a sensing element. Sensing element is fixed in the piston. Right? We need to capture the piston TDC point. Okay, using this sensor. You have two conducting elements. One of the element is fixed in the cylinder head. Other conducting element is fixed in the piston itself. Okay, and this conducting elements in this device are connected to an external circuit which consists of high frequency oscillator. Okay, and this conducting elements are subjected to an external applied electric field. So what will happen based on the piston movement? This device has to sense the piston movement. Okay, based on the location of the piston, the sensor output is going to be different because it changes the capacitance of the conducting element based on the piston location. These two conducting elements are separated by air. You know, air acts as a resistor, right? Dielectric substance. So you have air filled in between these two conducting elements. Based on the location of the piston, the frequency of oscillation is going to be different. Okay, when the piston is at TDC, here, so you have one conducting element fixed here, another conducting element is fixed in the piston. Okay, you have air in between which act as a dielectric substance. Now, based on the location of the piston, the frequency of oscillation in the sensor is going to be different. When the piston is at TDC, it is a closer point, right? That's why it is called proximity sensor. It is sensing how close the sensing element is. Sensing element here is a piston. Okay, the sensor is actually sensing the sensing element, how close it is. When the piston is at TDC, it is very close. it is going to generate maximum current in the external circuit. Okay, when the piston moves away from TDC, okay, the resistance increases, the current flow in the external circuit is going to be lower. So the magnitude of current flow in the external circuit is a function of the piston location, and the magnitude will be highest when the piston is at TDC. So this is how we sense that the piston is at compression TDC point by using this device, which is more accurate as compared to the static method, wherein you don't need any sensor. You are doing it manually based on the eye judgment.
Sir, just one question over here.
Yeah.
The sensor is connected on piston top also, sir, if I'm not wrong.
Yes.
Okay. So one will have the one sensor will be located at combustion chamber wall.
Not sensor. The sensor, everything put together is a sensor. Sensor consists of two conducting elements. One of the element is like a steel plate. Okay. One of the element is fixed in the piston. Other one is fixed in the cylinder head.
Noted, sir. Thank you, sir.
Sir, it is like a Hall effect sensor like that kind of.
What is it?
It is like a Hall effect sensor like that.
What is the Hall effect sensor you are referring here?
No. Hall effect. That
Hall
mechanism
effect.
Yeah.
Okay, so basically it is a proximity sensor in the sense that it is locating the sensing element where actually you have two elements, as I said. You are actually sensing how close the sensing element is. Sensing element is a piston here. Okay. So the sensor is determining how close the piston is located with respect to the sensor location. Based on the sensor sensing element location, the sensor output is going to be different.
Sir, is it like, are we moving the piston very slowly towards the TDC?
No, that doesn't depend on the piston velocity here. Okay, it doesn't matter. So what is important here is the distance between the two elements. When the distance between the two elements increases, the sensor output will drop. When the distance between the two elements decreases, the sensor output will increase and will reach a maximum when the piston is at TDC.
Okay.
Okay, so now what we are going to look at is we have discussed how to measure the cylinder pressure, how to measure the angle, crank angle, and how to reference the angle with the compression TDC point, which is a reference point for counting the angle. Okay, so we have discussed all this. Now we are going to see how we can derive several other parameters from the measured pressure profile. So far, using this measurement instrument, we have acquired the cylinder pressure profile. How the pressure varies with the angle is what we know by using this measurement instrument. Okay, with this measured data, we are going to see now what are the other parameters that you can derive, because only with pressure signal alone, you cannot do the combustion analysis. You need some other parameters, combustion parameters. So now let us look at how we can derive other combustion parameters from the pressure profile so that it will help you to do the combustion analysis. To do combustion analysis, you need, apart from pressure profile, you also need other parameters, combustion parameters. Now let us look at those parameters.
Sir, if I can ask one question, sir.
Hello?
Hello, sir. One question.
Yeah.
So, what will be the approximate crank angle difference between the Tmax point and the actual TDC, sir? Generally.
Okay, so in terms of magnitude, you are asking, right? What will be the? So you are asking about this angle, thermodynamic loss angle, right?
Okay.
So it will be less than 1 degree generally. It will be around 0.8 degree or so.
Okay, thank you.
So this is P theta diagram which we have acquired by using the instruments just now we discussed. We have recorded how the in-cylinder gas pressure varies with crankshaft angular position, considering compression TDC as a reference point. So any angle before this is negative, any angle after this is positive. So this is theta positive and this is theta negative during the compression stroke, and during expansion stroke it is considered positive. So this is what we have acquired. Now we are going to see what are the other parameters we can derive from the pressure profile. This is called pressure profile. Okay, so one of the information you can directly get from the pressure profile is this maximum pressure or peak pressure and its occurrence. This is one of the very important information, especially from the perspective of analyzing engine performance. This is P max, maximum pressure. It's one of the important information to do the combustion analysis. What is the value of P max will carry a lot of significance, because this is what is translating into work. The work that you get from IC engine is a function of this value, P max value. So there are two information here. One is the max value and other one is the associated crank angle. So this is associated crank angle. This is called occurrence, P max occurrence angle. Okay, so we need to know the occurrence angle and the maximum value of the peak pressure. And these two informations are derived directly from the pressure profile. Once you have this profile, once you plot this profile, you can directly take the P max value and the angle value from this profile. Okay, this is directly obtained. The other information that you can get from the pressure profile is the maximum pressure rise rate. Maximum pressure rise rate is based on the first derivative of the pressure profile. This is the slope you get. What is this vertical line? This vertical line is dP. What is this horizontal line? This is theta. So you have something called dP by d theta, which is a slope of the pressure profile, or first derivative of the pressure profile. Now, at a particular engine operating condition, this dP by d theta is going to be varying. As you could see from the profile, the slope is not linear, rather it's a non-linear value. Okay, the non-linear trend. So you will have different values, dP by d theta value. Among this, what is important for me is the max value at a given engine operating condition. When I say engine operating condition, it's a fixed load, fixed speed. At a given engine speed and a given engine load, there is one max value, one dP by d theta max value. That I can get by looking at the pressure profile, or I can draw the first derivative of the pressure profile, okay, which is dP versus d theta, okay. What is the change in pressure with respect to change in angle, crank angle? That is what is dP by d theta. There is one max value, that value I need to track. What is the significance of this value, dP by d theta max value?
It will decide the power of the engine, sir, in that way.
Power of the engine, anything else? We have already discussed.
Knock tendency.
Knock, exactly. So this is important from the perspective of analyzing knocking combustion. This cannot be too high. Okay, so you want a lower value of dP by d theta, but should not be too low. If it is too low, it means the burn rate is less, right? Deteriorated or poor combustion will result in very low value of dP by d theta, less slope. Less slope is an indication of less burn rate, less heat release. Higher value is an indication of better burn rate, higher burn rate, okay? But it should not be too high. If it is too high, you know, it will translate into combustion noise. Very high pressurized rate is what is combustion noise, and this combustion noise we discussed that will be there during knocking combustion. The noise is high, it is audible to human ear, okay? So we don't want a very high dP by d theta value. In fact, we discussed that there is a threshold limit. What is the threshold limit we discussed?
8 bars, if I'm not wrong.
8 bar, exactly. 8 bar per degree crank angle is the threshold limit. When it is higher than 8 bar per degree crank angle, we said the combustion will be classified as a knocking combustion. So what information I want to convey here is you need to track the value of dP by d theta max. Okay, maximum value of dP by d theta you need to track when you do a combustion analysis, because this is very important from the perspective of knocking combustion. So when it is too high, say above 8 bar per degree crank angle, you can infer that knocking kind of combustion is happening in the IC engine. Okay, that's why we need to observe and track the value of dP by d theta max. So this too you can get directly from the pressure profile. Okay, there are other useful information that you can derive. One of the useful information is apparent net heat release rate. Apparent net heat release rate. Now let us look at how we can get this apparent net heat release rate from the measured pressure profile. There is a simple derivation involved here to get the apparent net heat release rate. That is what I have shown here. So this is obtained by applying first law of thermodynamics to the closed part of the engine cycle. What is closed part of the engine cycle?
Compression, when the piston is at TDC in combustion chamber, if we consider.
Without intake and exhaust.
Intake wall closer to exhaust valve.
Yeah, so I have indicated here intake valve closer to exhaust valve open period. Closed part of the engine cycle is a period where both the valves are closed. Okay, that is a period where combustion is happening, right? When both the valves are closed. Combustion never happens when the valves are open. During the valve close period, combustion event is happening, right? Considering that we want to have an estimate of heat release rate. Pressure is directly measured, but the rate of heat release is not direct, cannot be directly measured. It's very difficult to measure the heat release directly. Okay, that's why we need to derive it from the pressure profile. Now we are going to look at how we can derive this heat release rate, which is a useful information about the combustion process. We are going to look at how we can derive this heat release rate from the measured pressure profile. Okay, to do that, we have to apply first law of thermodynamics to the closed part of the engine cycle, which is the valve close period, that is from intake valve closure time to exhaust valve open time, right? This is what is the closed part of the engine cycle, engine operating cycle. Okay, so when I say first law of thermodynamics, you know it is just an energy balance, right? We do when we apply first law of thermodynamics is just an energy balance. So what we are doing here, we are doing an energy balance for the closed part of the engine cycle to get the energy release or heat release rate. Okay, so you know in a engine, suppose if you consider a diesel engine, you spray fuel into the engine cylinder. What you have inside the cylinder? Air. When air and fuel are well mixed to the ignition limit, the ignition will start to happen and combustion will start to occur. Okay, the energy release due to combustion can be equated to, because of the energy release due to combustion, you have several other phenomena happening simultaneously. What we are doing here is we are balancing this energy release due to combustion with the associated changes. What are the changes that will happen because of energy release with combustion? One is there will be change in internal energy of the in-cylinder content, dU. So del Q combustion is equated to dU, which is what is going to happen as soon as the combustion event start. There will be change in internal energy of in-cylinder contents. So that is dU. Then the piston is producing work, useful work. The piston is moving down, delivering useful work. This is the only period where the work is positive, meaning the working substance, that is a gas inside the cylinder, expand and forces the piston to move down because of heat release due to combustion. The gases expand, force the piston to move down. So there is a delta W. Delta W is a useful work output that you get due to piston movement. This is called boundary work or displacement work, PDW work. Okay, this happens due to del Q combustion. So we are equating del Q combustion to change in internal energy of in-cylinder content, work that is extracted due to piston movement. Since you have not insulated the engine, you will have heat loss. Okay, occurring through the valves. Through the valves, heat will be transferred to the coolant. Okay, some amount of or the fraction of del Q combustion is lost to the coolant. That is what is the third term. And then there is a mass flow. There is an energy change due to the mass flow into the control volume. There are two mass flows happening. So when we talk about energy, we are considering mass flow and the associated enthalpy. One of the mass flow is through the spraying of fuel, that is dmF, and the associated enthalpy is H with the subscript F. So you have one mass flow due to spraying of fuel. That is associated enthalpy of the fuel mass. The other mass flow is happening through the crevice flow. Since you have a crevice, radial clearance between the piston outer surface and the liner, you have some mass flowing from the combustion chamber region to the crevice region. So dm with the subscript Cr is the crevice flow mass. H with the subscript Cr is the associated enthalpy of that crevice mass. Okay, so this mass will be a mixture of fuel and air. That's what is going to the crevice. Okay, so these two put together, I have indicated it as summation of dmi hi. Dmi hi is the energy associated with mass flow through the control volume and mass flow from the control volume. Okay, so that is sigma dmi hi. So the heat release due to combustion is equated to all these energy terms. One is internal energy term, second one work term, third one heat loss term, and the next one is about the energy term associated with the flow of mass into the control volume as well as from the control volume, which is summation of dmi hi. Now, when you consider all these four terms on the right hand side, this term, the value of this will be considerably low compared to the other three terms. That's why I have indicated this as negligible. So we will ignore this because of the lower magnitude. There's no point. For example, it's like adding 1 to 1000, something like that. It's very low magnitude compared to the other terms. So we ignore this. And I bring del Q loss to the left hand side. So it will be del Q combustion minus del Q loss. That will be equal to du plus delta W. Del Q combustion minus del Q loss. This is the gross energy released due to combustion, and you are subtracting heat loss from that, right? If you subtract heat loss from the gross energy released due to combustion, the associated heat is referred to as net heat. Okay, so the net heat is after the heat loss. The net heat del Q net. Okay, this term is replaced with del Q net because it is heat loss is excluded here. That will be equal to du term, the first term. Du can be written as mCV dt, and del W term, del W as I said, it's a displacement work. So you know W can be expressed as integral PdV. So when I say del W, this will be equal to simply PdV. So the second term is PdV term, third term is negligible. We have ignored this. So we are considering the first two terms. Okay, one is du, that is mCV dt. Second one is delta W, which is PdV. That is equal to net heat. Okay, net heat obtained during the combustion event. That is equated to this. Now I am modifying this mdt term. Okay, mdt term by using equation of state. You know this is equation of state. PV is equal to mRT, meaning that we are considering in-cylinder content as ideal gas. It's an approximation actually. Okay, so under what conditions this equation of state is valid?
Ideal gas.
The ideal gas equation is also called the equation of state. Under certain conditions,
Adiabatic conditions.
when the attraction this equation is valid. Right, considering that the temperatures are high during combustion, okay, the molecular attraction is less. So we are approximating in-cylinder content as ideal gas, okay, and then applying this equation PV equal to mRT. When you differentiate this PV equal to mRT, you can write it as on the left-hand side you will have PdV plus VdP because both P and V are variables. They are not constant. Okay, P and V are variables, so it is written as PdV plus VdP. On the right hand side you have mR, M and R are constant and T is variable, so you are writing it as dt. PdV plus VdP is equal to mR dt, and this can be modified to get mdt, which is what you have in this equation. I am replacing mdt with P and V. Why I am replacing temperature with P and V? There should be some logic behind this, right? So I want to get rid of this temperature. I am replacing this temperature in terms of pressure and volume.
So we have measured actually pressure.
Exactly. We have measured pressure and we can get volume through the slider crank relation, which we have already discussed. Once you have theta, you will get volume. So P and V are known information. T, temperature, is unknown. It's very difficult to measure the in-cylinder temperature. You can easily measure the pressure, but you cannot easily measure the in-cylinder temperature. Okay, that's why we get rid of T by taking this equation of state. Okay, mdt is now replaced with PdV plus VdP by R. This is what is mdt. The objective here is to get rid of temperature. So coming back to this equation, you have CV, you are retaining CV, you are replacing mdt with PdV plus VdP by R. Okay, that's what I have done here. Right hand side term I am retaining PdV term, which is from this delta W. So again, you have to be careful with the notations here. Observe the notations carefully. I have used D for internal energy, whereas I have used del for W. I have also used del for Q. What is the reason for this different notation for U, W, and Q?
Path and point function.
Exactly. So U is a property. Internal energy is a property. It is a point function. So you are using a finite symbol D. Del is not finite. Okay. So this W and Q are path functions. They are not properties. All these are different energy term. Please note that all these are energy term. Okay. But some of them are property. Some of them are non-property. Work and heat are non-property. They are path function. They are the function of the path followed in a process. Whereas U is internal energy is a property, it's a point function. It's a point function, not path function. Okay, that's why you use a simple D here for U and del for W and Q. So now del Q net on the left hand side is equated to MCV dt plus PdV. M dt is replaced with PdV plus VdP by R from equation of state, and I am retaining the CV. Right hand side term is as it is. Now I want to get rid of CV. I can express CV in terms of R. How do I do that? Again, you know this is a property relation between this CP, CV, and R. It's a fundamental relation that you should be familiar. I hope you know it. CP is specific heat capacity at constant pressure. This is specific heat capacity at constant volume. R is gas constant. These three are related through this relation. CP minus CV is equal to R. Right, and you know Cp by Cv is nothing but gamma. It's a ratio of the specific heats. So this is gamma. So I'm replacing the Cp and Cv with gamma by using this ratio. Okay, what I do here from this equation, I'm dividing this equation with Cv. If you divide this equation with Cv, you get Cp by Cv, which is nothing but gamma. The second term will be Cv by Cv, which is 1. That is equal to R by Cv. So I am dividing this equation with Cv. So you will get gamma minus 1 on the left hand side. Right hand side you will have R by Cv. Okay, from this I can write Cv as R by gamma minus 1. So coming back to this, Cv is now replaced with R by gamma minus 1, and you already have an R here. So this R will go off. Okay. That's why we are expressing Cv in terms of R to get rid of R, gas constant. Okay, so then you will get 1 by gamma minus 1 PdV plus VdP plus PdV. Simplify this, taking like terms together, PdV multiplied by 1 by gamma plus 1 by gamma minus 1 into VdP. If you simplify this, you will get gamma by gamma minus 1 PdV plus 1 by gamma minus 1 VdP. This is what is your del Q net. Now we are interested in finding how del Q net varies with the angle, crank angle. This is what we want to find the heat release rate with respect to crank angle, similar to pressure change with crank angle. So that's what I have written here. Incremental change in heat release rate with respect to crank angle can be written as del Q net divided by d theta, that is equal to gamma by gamma minus 1 PdV by d theta plus 1 by gamma minus 1 VdP by d theta. Okay, so this is the equation that you can use to get apparent net heat release rate. Apparent means approximate value of the net heat release rate. So you are getting this net heat release rate, okay, after excluding heat loss by using this equation, and this equation is obtained from first law of thermodynamics. So if you look at this equation carefully, what information you need to have? One is pressure, which is known to you from the pressure sensor. Second one is volume. Volume is known to you from the slider crank relation, and then change in volume with angle, change in pressure with angle. Since you know pressure change with angle and you know slider crank relation, you can get these two information. So this is known to you. P and V are known to you. Only unknown here is gamma. Gamma is ratio of specific heat. Generally, it varies between 1.3 to 1.35 during the combustion process. This is at the time of start of combustion. Okay, when the temperatures are high, it will be around when the temperatures are less, it will be high. It will be around 1.35. With higher temperature, it will be low. So the gamma value varies anywhere between 1.3 to 1.35. A good approximation is you can use around 1.32 or a mean value of this. Okay, that's the value of gamma that we use Okay, and from this you will be able to get the net heat release rate from the measured pressure value. Okay, so this del Q is derived from the measured pressure value by using this relation, and this relation is obtained by applying the first law of thermodynamics. Clear?
Sir, P and V are instantaneously measured at each and every point of measurement.
P and V are instantaneous values, exactly. P is at any crank angle and V is also at any crank angle. So you can even write, if you want to be more precise, this can also be written as P as a function of theta and V as a function of theta. These are instantaneous values, right? Clear?
Clear, sir.
Okay. It's time up. I will stop here. I will discuss about other parameters in the next class. If you have any questions, I can take your questions now.
Sir, is in the same equation, is dV by d theta arrived from the same graph, like inverse dV by d theta, sir?
dV by d, once you know volume, instantaneous volume I have discussed already. Just check.
So based on volume availability, this
instantaneous volume, okay. V theta, V as a function of theta, that is equal to Vc plus pi d square by 4 into y theta. Y theta is from slider crank relation, instantaneous piston position, that is L plus A minus S.
Yeah, thank you, sir. Got it.
So you know how V varies with theta from this equation. Okay, so you will get a profile like this. From this you can get dV by d theta. dV by d theta is nothing but the slope of this profile. So this is dV, like you have done for the pressure. Okay, this is dV, this is d theta.
Yes, sir. Clear.
Derivative of V theta profile. This is V theta profile. Like P theta, you have a V theta profile that is obtained from this relation. Slider relation. This is not measured, rather it is obtained from this relation. P theta is measured.
Yes, sir. Clear, sir.
Okay.
Sir,
Yes.
So, not related to this. This is regarding the current engine market trend, sir.
Current engine, or what is the question?
Current engines in the market, sir. One general question. So we see now, of late we are seeing PFI engines coming with dual injectors. What are the advantages of having dual injectors for a PFI engine?
Can you be a bit louder? You are asking about what are the advantages of dual injector, right?
Dual injectors for a PFI engine. We are currently seeing engines with dual injectors in the market. So,
dual injectors, dual PFI injector or dual injector for a DI case?
Dual PFI injectors. Say Maruti is Maruti are having dual PFI injectors. What advantages?
Dual PFI injector for SI engine, Maruti passenger car.
Yes, sir. Yes, sir.
Only advantage I could see, there is a complexity definitely. If you go for two injection system, it is an add-on. Okay, so you need to have additional control with the two injection, but with each injector there is an additional control system. Okay, so it is an add-on cost. What benefit you will get if you ask me? You are actually using two injector, you are reducing the duration of injection. Right? Suppose if the duration of injection with one injector is say 20 degree, with two injector you can done with 10 degree.
Okay. Okay, sir.
Okay, so, same mass or volume that you are injecting, you are actually reducing the time at which the fuel needs to be injected.
Okay, sir.
Other than that, I don't see any big advantage here, because anyway it is anyway it's a good, it's a highly volatile fuel. There is no problem. So I don't see any problem of mixing related issues addressed here, because it's taken care with taken care by the fuel, which is a highly volatile fuel. It can provide a homogeneous mixture. Only advantage is the duration is shortened by half.
Okay.
Duration of injection.
Okay, thank you. Just want to understand if there is any additional benefit.
So when you shorten the injector duration, actually you can say that the mixing is improved to some extent, but I am not sure how it improves the engine performance directly. right? When you inject for a longer duration and a shorter duration, the advantage is so you are providing better mixing. Okay.
Okay, sir. Thank you. Thank you.
It's like a split injection. When you give more time, when you give more time for mixing, you would expect the homogeneity of the mixture to be improved.
Okay, sir. Thank you.
Fine.
Sir, just to add to what Vivekanand was saying, in two-stroke engines in ships, we have minimum 2 or even 3 injectors for each cylinder. Sorry, for the older mechanical type engines, we have all the 3 injectors injecting as per the cam shift. I mean, based on the cam peak, and because that is basically for having the spread of fuel across the cylinder, because the bore size is much bigger, because we have up to 980 cylinder bore size. But the recent electronic engines where the fuel injection timing is controlled by the crank angle sensor, there the injectors will partly inject. That means, sir, for lower RPM of engines, because here we consider RPMs, the maximum we reach is only 100 or
for marine engine, yes.
Yes, sir. So until 25 or let's say 30 RPM, only one of the injectors will be injecting on a cyclic basis, because we cannot have only one injector, because the other fuel injectors will get clogged, because we have heavy fuel oil, sir. And once the RPM rises and the load increases, then all the 3 injectors will start injecting, sir. So in this way, the amount of fuel consumed is reduced, and it helps in the better scavenging process also, sir, during the low load operations, where the mean speed is also lesser, and also the scavenger pressure is also lesser. So the scavenging process will not happen effectively there, sir.
So this is a 2-stroke engine, right?
Yes, sir. Correct, sir.
2-stroke, and injector is mounted in the cylinder head, right?
Correct, sir. Correct, sir.
Okay, so in actually in marine engine, the problem is the heavy fuel, as you said.
Correct, sir.
It's a high viscous fuel, almost 10 times higher viscosity than diesel.
Correct.
So mixing is one of the problem in with such a high viscous fuel, which is just opposite to gasoline. Just now I said that you don't have any critical problem or critical issue of mixing or homogeneity. Whereas here that is a critical problem, because it's a heavy fuel. And splitting the injection or using multiple injector definitely will improve the mixture homogeneity. That's one thing. And second one, the fuel mass, as you rightly said, when you move towards high load, you are using all the 3 injector, because you are taking high load. The engine is run at high load only with higher fuel mass, right?
Correct,
so the quantity of fuel to be injected is so high, meaning if you use one injector, the duration of injection is going to
also shortens at the higher RPMs, as compared to the lower RPMs.
Yeah. Higher and lower in the relative sense you are talking, 20 to 100 RPM, right?
Correct, sir. Yes, sir. But although it's a short range, the load, like every RPM, it's around 300 to 400 kilowatt increase of load, sir. So there we have a load limiter program. Even when we want to increase the speed, it is on a load limiter. So the cylinder lubrication will be kept very high. Normally, it's around 3 to 4 grams per kilowatt hour. And then once the load settles is when the cylinder lubrication will come down to normal range, which is around 1 grams per kilowatt hour in those engines. Yes, sir.
Okay. So there definitely using multiple injector or split injection will improve. Even split injection won't help much, because the volume of fuel handled is so high in a marine engine.
Yes, sir.
So having multiple injector will definitely help. But for SI engine with gasoline kind of fuel, exact benefit I'm not sure what benefit you will get by having multiple PFI, because mixture homogeneity is not a major issue, and the volume of fuel injected generally is very low. Compared to marine engine, even in a passenger car, it's low only. So you can meet with only one injection system.
Yes, sir. So maybe that gasoline engines, the multiple injectors is provided as equivalent to the CRDI, sir, because in CRDI we have the fuel injection happening in different phases, pre, main, post, and after. So that because we had this topic in autonomous vehicles as well.
No, again, CRDI multiple or split injection. The primary objective is to improve mixing and reduce pollutant emission.
Okay, sir.
Split injection is done pilot main, or even you can go with 5 pulses. We call it as pulses, right? Number of pulses can even go up to 5, I think. And the main advantage or primary advantage there is you improve the mixing with multi-pulse instead of single pulse, and that improved mixing will reflect in lower emissions.
Understood, sir.
Pollutant emissions are reduced considerably.
Okay, sir.
That is the diesel-like fuel, but with gasoline-like fuel, whether any improvement in homogeneity brings emission benefit, I am not sure. I need to analyze the data to comment on that.
Understood, sir. Thank you, sir. Thank you.
Okay, fine.
Sir,
Okay.
one last question. Sorry, I'm sorry to. Sir, one last question. Basically, in the SI, while taught us that knocking in SI engine, you had told us that if the end gas is getting ignited, self-ignited, so that is the phenomenon of knocking, which can damage the engine in that sense. But you had also told that the surface ignition can also happen sometimes, right, sir?
Yeah.
Surface ignition and end gas, knocking into end gas self-ignition, both are distinct phenomena, if I'm not wrong, right, sir?
Both are different phenomena, definitely.
Okay, sir. Got it, sir.
Surface ignition is untimed ignition, okay, and knocking is happening at the end of combustion. Surface ignition is happening at the start of combustion.
Okay, sir.
Damage is severe when the self-ignition happens near the end, because the intensity of energy release is very high, way high, compared to surface ignition, which happens at the start of the combustion event. But what will happen, these two will go together. I mean, if you allow knocking for a prolonged period, the surfaces will reach high temperature. When the surfaces reach high temperature equivalent to self-ignition temperature of the given mixture, it is going to create pre-ignition.
So if my cooling system is also deteriorated in some way, like if my
so this two goes together in the sense that eventually it is going to damage the engine. Pre-ignition will lead to knock will lead to pre-ignition. This is what I mean by these two will go together.
Right. Thank you so much. Thank you so much.
Fine. So I will stop here. I will see you tomorrow at 6 o'clock. Thank you.
Thank you,
Bye.
sir.
Very good.